In this video, we consider the reverse reaction of enamine formation, namely the hydrolysis of enamines, which, just like the hydrolysis of imines, takes place under acidic condition. Okay, so our net reaction is we have our enamine, and for sake of being clear, I will use the same enamine that I formed in the last video. We are reacting it with water, again in the presence of H+. Catalytic amount of H+ is all that's necessary, and that takes us back to the aldehyde plus the secondary amine. So most of the mechanism is very similar to that of imine hydrolysis, but the first step is very different. Okay, so step one of this mechanism, instead of protonation on the nitrogen, is protonation of the carbon-carbon double bond to give an iminium ion. Okay, so this is the first example you have seen of a pi bond acting as a Bronsted base. So if we follow what's going on with the arrows here, the lone pair on the nitrogen is still the ultimate source of the electrons. So we take the electrons from that lone pair and use them to form a CN pi bond. Now we have to break another bond to the carbon, or else carbon would have more than 4 bonds. So we take the electrons from the carbon-carbon pi bond and we use them to form a bond from the next carbon over to the hydrogen of H3O+. Okay, and then a third arrow is necessary to break the hydrogen-oxygen bond of H3O+ and generate H2O. So what's fundamentally happening is that the pi electrons of the carbon-carbon pi bond are transmitting the nucleophilic character of the nitrogen to the carbon 2 atoms away. Okay, so this is how we end up with the hydrogen going onto the carbon rather than onto the nitrogen. Now, you may ask me, can this structure protonate directly on nitrogen? And the answer is yes. Will that get us closer to the products? The answer to that is no. Okay, so why is that the case? Why is protonation on nitrogen not helpful? Well, protonation on nitrogen would lead the structure depicted on the screen, in which you have nitrogen forming 4 bonds and a positive charge. So if you've been following through these mechanisms, you would think, okay, that nitrogen has to leave to get us back to the aldehyde product. Can't we just expel dimethylamine as a leaving group? That is a reasonable assumption based on what you know. It turns out not to be correct. And the reason it turns out not to be correct is that would yield a vinyl carbocation. In other words, the positive charge is directly on the CC double bond, which is extremely unstable. So therefore, that step is not reasonable. You can't have a vinyl carbocation. Furthermore, 2 other things need to happen in addition to expelling dimethylamine to get us closer to the aldehyde product. First of all, the carbon-carbon pi bond needs to be broken. The final product we're going to here does not have a carbon-carbon pi bond. And second of all, the hydrogen needs to be put on that carbon containing the 2 methyl groups. So using the pi bond as the immediate base, supported by the lone pair on the nitrogen, achieves both of these objectives in a single step. The remaining steps of this mechanism are now exactly the same as what we saw previously for imine hydrolysis. We've gotten to the iminium ion. Now getting from the iminium ion back to the aldehyde plus amine is familiar territory. Okay, so once we have the iminium ion, that is electrophilic at the carbon of the CN double bond, and that gets attacked by water. We have plenty of water around. This is a hydrolysis reaction. Just in case you needed another molecule of water, you generated it when you protonated the CC double bond. Okay, one arrow from the water to the carbon, another breaking the carbon-nitrogen pi bond, putting those electrons back onto the nitrogen. Okay, now we have a positively charged oxygen. So what we have to do is do our intramolecular proton transfer from oxygen to nitrogen, because after all, that nitrogen does have to end up becoming the leaving group. We've made a good leaving group. Now we allow that leaving group to leave, which generates the resonance stabilized oxocarbocation. And working from the second resonance structure, which already has the CO double bond, we can simply deprotonate it, and that takes us back to the aldehyde that we want to get to as the final product of this reaction. Okay, so most of enamine hydrolysis is the same as imine hydrolysis. The difference is the first step. Just like most of enamine formation is similar to imine formation, whereas the difference is the last step.